let's go on to the second fundamental theorem of calculus. This allows us to do some really neat and cool things. Let's look at integration when we went from lower integrand to upper integrand, from a constant to a constant, and f was a function. This gave us a definite integral. This definite integral gave us a number. It might not have been a pretty number, but it was a number. For the second fundamental theorem of calculus, now we're going to talk about f of x equaling a function of x, where we're going to integrate from a to x, or a to a function of x, of some f of t dt. Now, all we've done is we've changed this. This is usually a dummy variable. It doesn't matter what your variable is. But when you get out of this, you're going to wind up with a function in x. When over here, we always got a number. Now let's look at this. Suppose we're looking at the integral of f of x, or f of x is the integral from 0 to x of cosine t dt. We're going to look at what happens to this as you increase what x is. Now clearly when x is 0, this is the integral. Let me switch over here to my pen. At 0, all right, f of 0 is the integral from 0 to 0 of cosine t dt. Well, that's just 0. I mean, this is a sketch of my cosine function. All right. So what happens now if I decide to let x equal, oh, I don't know, let's try pi over 6. All right, what will this look like? Well, let me move this. Let me move this up. I see that I'm going to come down here to pi over 6, and it's going to be this area right here. All right, or it'll be about 1/2. What if I then decide to integrate to x equals, oh, I don't know, pi over 4. And then x equals pi over 3. And then x equals pi over 2, where here's pi over 2. Now, in all of these cases, I'm accumulating bits of this function. Let me go on and do this integral. F of x is the integral from 0 to x cosine t dt. The integral of cosine is sine of t evaluated at 0 and x. So this is sine of x minus sine of 0, or it's just sine of x. So as I change what x is, you see I am accumulating this function. Let me move this over here. All right, so it goes from, at f of 0, the function is 0. But as I move across, you see how I'm simply accumulating more and more of the sine function. All right, we are going to discuss in a bit this being an accumulation function. So basically we can evaluate this function at any x, and we could go through and do the computations. Try this one. Stop the tape when you're done. Turn it back on because we're not finished yet. Now let's look at the second fundamental theorem of calculus. It's a really, really interesting theorem. It says, suppose I have a function f that's continuous on an open interval containing a. Okay, so, a, we can call this x. For every x in the interval, the derivative with respect to x of the function of the integral from a to x of f of t dt is equal to f of x. Let's look at this proof. Let's define f of big X to be equal to the integral from a to x of f of t dt. All right, it'll be easier to write. Now, let's look at the derivative of f of x. All right, we know from the definition this is the limit as delta x goes to 0. Oh, yes, you're remembering this now, aren't you? Of f of x plus delta x minus f of x divided by delta x. All right, now what I'm going to do is I'm going to, let me just pull out this 1 over delta x here. All right, and I probably should leave my limit in, shouldn't I? Limit as delta x goes to 0. This is equal. Now, f of x plus delta x, all right, everywhere I have an x here, I'm going to replace it with x plus delta x, is the integral from a to x plus delta x of f of t dt minus f of x, which is just the integral from a to x of f of t dt. Okay, we're in pretty good shape here. Now I don't like this negative sign here, so let me get rid of it. So this is the limit as delta x approaches 0 of 1 over delta x times the integral from a x plus delta x f of t dt. Now how do I switch this? I just switch the limits of integration. So it's plus the integral from x to a of f of t dt. Now, because these limits are the same, I can combine this. This becomes the limit as delta x goes to 0 of 1 over delta x. Now, this becomes the integral. My lower limit is x. My upper limit is x plus delta x, f of t dt. Cool. All right, from the mean value theorem, we know there exists, and we're just going to assume delta x is positive at this point in time. There exists a number c that is contained in the interval x plus delta x, all right, such that the integral for the expression is equal to f of c times delta x. Now, since I also know that x is less than or equal to c, and that's less than or equal to x plus delta x, it's very clear that as delta x goes to 0, c goes to x. So let me rewrite this. F prime of x is the limit as delta x approaches 0 of 1 over delta x times f of c times delta x. Oh my goodness. So this just does cancel. So this becomes just f at x. Now, let's use the second fundamental theorem of calculus to do some calculus. Evaluate d dx of the integral from 0 to x and the square root of t squared plus 1. Let's put a dt in there so we're mathematically correct. Now, let's you don't have to do this every time, but let's let f of t equal the square root of t squared plus 1. Now that is continuous on the entire real line, so we can use the second fundamental theorem of calculus to say that this derivative, 0 to x of the second square root of t squared plus 1 dt is equal to, let's see, that's just x, so this is going to be the square root of x squared plus 1. Kind of straightforward. Now we can throw you a curve. What if the limits of integration aren't just x? What if they're a function of x? Well, we can use a chain rule to help us out. Let me let u equal x cubed. All right? Now I know f prime at x is equal to df du times du dx. Now, I also know that d du of f of x, now this is kind of my definition here, du dx is equivalent. Now I'm going to substitute in f of x is this integral. So this is d du of the integral from pi over 2 to x cubed of cosine t dt. And this is all going to be times du dx. All right. Now, at this point in time, let me substitute in. I'm doing a derivative in u, so let me substitute in what u is. So, this is d du of the integral from pi over 2. Now, u in this case is x cubed, so that's just u, cosine t dt times du dx. Now, from the second fundamental theorem of calculus, I know this is just cosine u. Now, times du dx. Now I need to figure out what du dx is, isn't it? Du dx is 3x squared. So, taking all of my conversions, going back from u to x, this becomes cosine u is x cubed. Du dx is 3x squared. So this becomes 3x squared cosine x cubed. Done. Now try these. When you're done, stop the tape. Enjoy your evening. Finish your homework.